Welcome to our lecture on materials science, focusing on creep and stress corrosion. These phenomena are critical in understanding the mechanical properties and failure mechanisms of metals. By the end of this class, you will be able to explain the conditions and mechanisms leading to major types of metal failure, including creep failure due to prolonged high temperatures and stress corrosion cracking from liquid-induced cracking. Let's test your understanding. Ductile materials should be loaded in tension, while brittle materials should be loaded in compression. Take a moment to think about why this is the case. The correct answers are: ductile materials should be loaded in tension, and brittle materials should be loaded in compression. This is due to their differing mechanical properties and how they respond to stress. Creep failure occurs at high temperatures due to slow elongation. Here, we see sample deformation at a constant stress over time, highlighting primary, secondary, and tertiary creep stages. Turbine blades operate under high temperatures and elevated stress, requiring unique materials and microstructures to withstand these conditions and prevent creep failure. Different materials exhibit varying strengths at high temperatures. Nickel alloys, for example, maintain their strength better than steel or aluminum alloys, making them ideal for high-stress applications. To predict creep failure, we use tests involving constant stress and high temperatures. Mechanisms like grain boundary sliding and dislocation climb are critical in understanding material deformation. Dislocation climb is a key mechanism in creep deformation. It involves the movement of dislocations within the crystal lattice, allowing materials to deform under constant stress. Consider these statements. Creep is a thermally activated process. Primary creep rate increases with time, and as temperature increases, the time to failure decreases. Reflect on their accuracy. The correct answers are: creep is a thermally activated process. Primary creep rate increases with time, and as temperature increases, the time to failure decreases. These principles are fundamental to understanding creep behavior. High-temperature creep failure involves mechanisms like grain boundary cavity formation, grain boundary sliding, and dislocation climb. These processes contribute to material degradation under stress. Stress corrosion cracking occurs at low stresses due to environmental agents like saltwater, which enhance grain boundary cracking and lead to material failure. Environmental agents such as saltwater can significantly reduce the critical time for cracking in metals, emphasizing the importance of understanding stress corrosion mechanisms. Artificial hip replacements can fail due to corrosion from contact with body fluids, leading to crevice attack and stress corrosion cracking. Proper material selection is crucial to prevent these issues. Corrosion failure can occur in various forms, such as pitting in stainless steel or stress corrosion cracking in brass. Understanding these mechanisms helps in designing more durable materials. To recap, we've explored the conditions and mechanisms leading to metal failure, including creep and stress corrosion. These insights are vital for improving material performance in various applications. Thank you for watching. Please like, share, and subscribe to our channel. Leave a comment below about what you learned and what topics you'd like to explore further. This presentation contains copyrighted material used under the Fair Use Doctrine for educational purposes. Links to relevant resources are provided in the video description.